Alright, so now we're going to talk about solutions with dissolved gases. There's a trend here. It's just different phases of matter and how they dissolve. And every phase of matter kind of has its own set of rules. So you got to be aware of what you're dissolving. Alright, so solids was the last video. Now we're talking about gases, temperature relationships, pressure relationships, intermolecular forces, all of that. It's a whole new slate. We got a blank slate. The rules are going to be very different. So you've got to be aware of what type of solute you're dealing with, because the rules are going to change, unfortunately. Now, I say that in terms, and I mean this in terms of different phases of solutes. So solids, the general terms I talked about, you're good. You're dissolving a solid. What I talked about there, you're in good shape. Gases, you're in good shape. When I talk about liquids, you're in good shape. But if you mix up your rules and you start applying solid rules to dissolving a gas, you're going to be in big trouble. It's not going to work. So I'm just giving you an early heads up on that. Now, sometimes it seems a little bit weird to talk about dissolving gases, but they do dissolve in liquids. Okay, so they, you don't just you get out your nitrogen shaker and then shake some nitrogen in there and stir it around and get it dissolved. It's a different process, but it's one that's incredibly important to survival of all of life on Earth. We depend on dissolved gases. So we need gases to dissolve in our bloodstream. We need CO2 and oxygen gas to dissolve. We have proteins to help with that. Shuttle around oxygen. Hemoglobin. But it does need to float around on its own as well. So the example I like to give, because biology is gross, and now I've alienated all of my biology students, and they're going to tell their biology professors that I need to have my employment terminated at the college because I'm an anti-biologist. That's not true. It's all zebras to me. Remember the fun times? Alright. So, carbonated beverages, because that's cooler than biology. I know I've done it. I really shouldn't do this stuff on camera. This is more of a live version of what I do. It's alright. All biologists don't like chemistry either. So we all appreciate that we enjoy what we do, but we do not understand why the other person enjoys what they do. Alright? And so a carbonated beverage it's dissolved CO2. So I guess, in theory, if we made enough Coca-Cola, we could get all the extra CO2 out of the atmosphere. We just could never open the cans. Alright, so there you go. Crisis averted, everybody. So it's dissolved CO2. And so when we think about dissolving gases, what we can think about is, how do we keep a carbonated beverage from going flat? How do we keep all the CO2, all the bubbles from escaping? What do we do? And the answer to that question is the same as, what do we do to get gases to dissolve? So, what do we do for temperature? Do you like to drink a hot glass of Dr. Pepper in the morning? Or is it something you want to keep cold to keep it carbonated? So does it stay carbonated if it's hot or cold? The answer is we keep it refrigerated, right? So, decreasing temperature is going to give us an increase in solubility. And the reason is just that if the gases have more kinetic energy, they're less likely to be in the liquid. So when they get dissolved in liquid, they're going to interact with other liquid molecules, but they can rocket out of there, just like when something evaporates. If it gets enough kinetic energy, it'll leave the liquid. Same with something that's a gas, except for it takes even less of a difference in kinetic energy to do that. So, we keep drinks cold to keep them carbonated. Well, you keep a solution cold, you're going to keep gases dissolved more. And then we will talk about pressure at the end, and in the middle we are going to talk about intermolecular forces. Now, gases don't have very strong intermolecular forces. If something gets a gas at, say, room temperature, room pressure, or atmospheric pressure, it's not going to really interact with its neighbors much. It's just going to kind of move around the container, bounce around. It's not going to catch and form a liquid, right? It's a gas. And so what does that mean by not catch and form a liquid? It means not strong attraction, not strong intermolecular forces. So most gases And then again, this is at standard temperature and pressure. If it's a gas that in the room with you now, it's probably only going to have dispersion forces. There are exceptions to this. Sometimes they can be polar. But, stuff like oxygen gas, hydrogen gas, helium, nitrogen gas, all that stuff, argon, whatever, are just dispersion forces. And so, as we get an increase in dispersion forces, which means, an increase in gas particle size. So for example, oxygen is bigger than hydrogen. It's going to have greater dispersion forces. And so as that happens, we get an increase in attraction to the solvent. Which equals a greater solubility, because the solute attraction is really, 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 really low. And so it's really just all about this. And so we can actually talk about a trend here. So stronger IMFs for gases equals stronger solubility. And if the intermolecular force of the gas gets so strong that it would break this trend, that thing's not going to be a gas at standard conditions. It's going to be a liquid or a solid. And so then it goes on a different video. It's not our problem right now. Alright? So, as an example, O2 has stronger IMFs than H2 because it's bigger. Oxygen atoms are bigger than hydrogen atoms. Now, how do you know something's bigger or not? Well, as you go down the periodic table, things get bigger, and as you go left to right, they get smaller. So oxygen would be, smaller than nitrogen, but it has more electrons, so it gets dicey. But hydrogen is definitely, H2 is definitely smaller than O2. So I won't really worry about the gray area stuff. H2 is smaller than O2. So, if O2 is larger, it has stronger IMFs. So O2 is more soluble. More of it's going to dissolve than hydrogen in a given amount of water. Alright, so in the event of a polar gas molecule, that's going to be even more solar, or even more soluble. Solar. It's going to have greater than anything with just dispersion forces. Because again, it's just increases in IMFs. It's not just dispersion forces, but IMFs in general. Just most of them only have dispersion forces. But if you do have something that's a polar gas molecule, they're going to have even greater solubility. Alright, and so the example here, HCl is a gas. It is very water soluble. It is polar. And so it's going to be more soluble than O2. Now, this is complicated a little bit because HCl doesn't just stay HCl when it dissolves. It becomes a strong acid and it goes H plus Cl minus. So that actually helps stabilize it and make it even more soluble, because now HCl's aren't bouncing back out of the liquid because they've separated. So they're kind of like stuck there. They don't just reassemble and leave very easily. So in the event of something that's an acid, if the gas can behave as an acid in solution, it becomes even more soluble on top of that. But we're not going to worry about that too much. It just happens to be that was the polar molecule that I thought of it as the gas. And then afterwards realized that there is an extra complication there. So, sometimes there's kind of layers to this chemistry. Can't always be a simple example, unfortunately. Alright, so keeping it cold increases solubility. Having stronger attractive forces means it's going to catch in the solvent easier and be more soluble. Alright, so what about pressure? Remember, solids did not have a change in solubility because they're not compressible. Well, guess what gases are? They're compressible. You increase pressure, they change volume. And you can have big changes in volume. So you can actually push gases into liquids. So as you decrease the volume available to the gas, more and more of it's going to be dissolved down here in the liquid. It's just there, you can actually push it in. And that's how you carbonate a beverage, is you hit it with really high pressure CO2, and it dissolves in, and then you cap it, and it can't escape. And if it does, it pressurizes at the top and starts to dissolve again. So that's why keeping a cap on will keep it carbonated, if it's a soda or something. So increasing pressure equals increasing solubility for all the reasons I just talked about. In addition, we can model this with Henry's law. Named after King Henry VIII, because he's a very gassy fellow. Nah, that's not. I don't think that's why. I don't think it's... What are the odds, right? There's quite a few. I had like a great-grandfather Henry, so there's a lot of them. So, here's the formula. We'll break down the pieces. So this is our concentration of the gas that's dissolved. Okay. K, can't spell constant without K. This is Henry's law constant. Sometimes it's known as K sub H. And that's going to depend on the gas, what molecule it is. And temperature. Every now and again I have a student that loses their mind. They cannot handle a constant that varies with another variable. Okay, so it's a constant at constant temperature. Okay, it's weird, I know, but generally we're working at, STP or standard, at least standard temperature. And then P sub G is pressure of the gas. And so if pressure goes up, concentration goes up. If pressure goes down, concentration goes down. Because remember, K is fixed. And so it's nothing too crazy. It's a linear relationship. It can get more complicated than this, but we're not going to worry about it. Like, this is kind of like our ideal law, or it's like our ideal gas law for this situation. We're going to stick with it because it's very friendly. There's some other stuff we go to when it doesn't work. We're not going to worry about that. Not this week, anyway. So, for example, what is the solubility of CO2? In water at 25 degrees Celsius and 2.5 atmospheres if K equals 3.1 times 10 to the minus 2. Here's some fun units for you. Molar per atmosphere. Under these conditions. Okay, how did I know what K was? I looked it up on a table. Yeah, that's right, that's what you do. Unless you're given the other variables. So that's the thing, right? There's two variables and a constant. Tell you one, you solve for the other. If you know both the variables, you can determine the constant. So you should always know 2 out of 3 here to solve it. In this case, we know K, we know P, Alright, so that means our C of our CO2 is going to equal our K, which is 3.1 times 10 to the minus 2 molar per atmosphere, times my pressure of 2.5 atmospheres. And that comes out to be 7.8 times 10 to the minus 2 molar. So my atmosphere and per atmosphere cancel out. Oops, sorry, got lost in the corner there. And there you go. That's your concentration. Not a very high concentration, but if I double the pressure, make it 5 atmospheres, I'll double the concentration. My beverage will be even more carbonated. Alright, so with gases, it's a different rule set than solids. Alright, so now we want to keep temperature down to keep the stuff dissolved. And we can up the pressure, and we can compress more gas in there. And we can talk about a trend with intermolecular forces because gases don't interact with each other. There's no pure solute IMFs we have to worry about. And so it's just, what's the interaction with my solvent down here? The more favorable it is, the more of it's going to dissolve. And that's the only thing we have to worry about with IMF. So very straightforward with gases, because half of it just gets thrown out. We don't have to worry about solute-solute interactions, because there are none, because it's a gas. Alright, so we're going to talk about liquids next, and then we are done for the week. You know, have a happy Thanksgiving, and if I'm ever reusing these videos in spring, it's mandatory. You're going to have to celebrate Thanksgiving that week as part of your homework, okay? It's the only way. To make up for all of the, at least this Thanksgiving, that most people don't get to celebrate with anyone else, alright? You know, you have to like argue with your mop that you set up at the other end of the table, you know, that has some sort of disagreement that goes back generations in your family or something. Alright, so liquids next, and that'll be it.